All right, hello and welcome to day 7. Um, like I saw yesterday, the problems are starting to get a little bit harder. The straightforward uh, solution seems to break down in part 2. So excited to see what happens on day 7. So day 7, the treachery of whales. A giant whale has decided your submarine is its next meal, and it's much faster than you are. There's nowhere to run. Suddenly, a swarm of crabs, each in its own tiny submarine, it's too deep for them otherwise, zooms in to rescue you. They seem to be preparing to blast a hole in the ocean floor. Sensors indicate a massive underground cave system just beyond where they're aiming. The crab submarines all need to be aligned before they'll have enough power to blast a large enough hole for your submarine to get through. However, it doesn't look like they'll be aligned before the whale catches you. Maybe you can help. There's one major catch. Crab submarines can only move horizontally. You quickly make a list of the horizontal position of each crab, your puzzle input. Crab submarines have limited fuel, so you need to find a way to make all of their horizontal positions match while requiring them to spend as little fuel as possible. For example, consider the following horizontal positions: 16, 1, 2, 0, 4 to 14. This means there's a crab with a horizontal position of 16, a crab with a horizontal position of 1, and so on. Each change of one step in horizontal position of a single crab costs 1 fuel. You could choose any horizontal position to align them all on, but the one that costs the least fuel is horizontal position 2. Move from 16 to 2 is 14 fuel, 1 to 2 is 1 fuel, 2, etc. This costs a total of 37 fuel. This is the cheapest possible outcome. More expensive outcomes include aligning at position 1, 41 fuel, position 3, 39 fuel, or position 10, 71 fuel. Determine the horizontal position that the crabs can align to using the least fuel possible. How much fuel must they spend to align to that position? Okay, so let's start here. Let's get the puzzle input and start thinking through possible solutions. Let's say puzzle problem input. And we've also got test input. We'll probably be putting this in the test, but just in case we don't, just take care of it. Okay, so let's see. We've kind of got a crab submarine seems like one of the objects that we've got. And then we've also got crab submarine, so you need to find a way to make all of their horizontal match, requiring them to spend as little fuel as possible. It seems like maybe they can use as much fuel as they want, but we want to use the least total fuel rather than the least fuel each. So there's no maximum fuel. Crab a crab submarine. Okay, so let's start there. Let's just model out the crab submarine for a start, and it should be pretty simple, and then we can figure out what we're going to do for the system, or what is swarm. Yeah, so there's a swarm of crab submarines, so it's a submarine swarm is the other object. Submarine swarm. Seems like a good name, so we'll test that out. And submarine swarm will be the one that figures out the least fuel. Okay, so for crab submarine, require relative crab submarine.rb and describe crab submarine. And crab submarine is going to have an instance method that so crabs are going to have a position, and then they're going to have a cost to get to that position, to get to a new position. Let's see if there are any good words that stick out. Limited fuel. Each change of one step in horizontal position of a single crab costs 1 fuel. 0 to 2. Okay, so they can go left or right. So cost to, and then they're going to have a position. So let's create a couple here. So context. Starting at position 16 and context starting at position 0 and context. Those two positions seem all right. Starting at position 16, moving to 2, at position 2, moving to 2, and so this one, it is 14. Fuel cost 2, 14, and so it is 14, so here we do test crab submarine equals crab submarine dot new, and it's going to take a position, take a starting position, and then we do expect test crab submarine dot fuel cost to 2 to equal 14. And then here it is 2. And so I picked this one because we're going to be going up. The first one we're going down. And we can copy this same test body, but with just different numbers. 0, fuel cost to 2 is to equal 2. Okay, and so that fails. Initialize constant. Class crab submarine. Initialize starting position. And we're going to expect these to be ints coming in, so starting position equals starting position, and let's test that out. Okay, find method fuel cost 2. And these are going to fail because of that. So the we did that in a previous problem. We really just want to get the absolute value of that. So actually I want to put another test in here. Starting at position 2, it is starting at position 2, moving to 2, it is 0. I just like to get all the different cases to make sure that I'm not missing anything here. Okay, it's the same body. And 2, move to 2 to equal 0. And the fuel cost 2 is at position minus position dot ABS. Let's see where we're at. All 3 passed, cool. So now we've got this submarine object that we can start doing stuff with. Well, then we've also got a submarine swarm and submarine swarm spec.rb. And so that require rspec, require relative submarine swarm b, describe submarine swarm. Actually, we probably also need to I'm going to be using the Krebs submarines in these tests because the submarine swarm is going to take a oh, I guess maybe not. No, maybe we'll create the interface that it takes that it's initialized with nothing, and then we add the swarm. That way it's I don't know, maybe the interface is a little bit easier to use if you just give it a string of swarm positions or submarine positions, and then it creates them. I guess we'll see. So this is, we're going to get the cheapest possible outcome. More expensive outcomes include aligning at position 1, position 3, position 10. Okay, so that's pretty neat. I kind of might want to have, it's going to give me a little bit more testing options here. The first thing that jumps to mind is we can check the min position to, we kind of need to check all the positions, right? To the max, because it'll never be better to go over the max and never be better to go under the min. So it's probably somewhere well, okay, so what we need to do is total fuel 2. Let's say we've got a method total fuel 2, and it's going to take a position, it's going to check the swarm and tell how much fuel total to get to that position. Okay, so we've got test swarm equals submarine swarm dot new, and we can, let's just use this string here so we don't need to input that file. And then we want, actually we can change that to what we did yesterday. Test swarm, so we're just going to use this same same object in all of our tests, but want to get it, use it brand new each time, we can just set that there, and we're going to write all our tests against that. So total fuel 2 context, or context moving to, it is 41 when moving to position 1. It is 39 when moving to position 3, and it is 71 when moving to position 10, and it is 37 when moving to position 2. Okay. And so then we can just do test swarm expect test swarm dot total fuel to 1 to equal 41. Okay, and then 3 is equal to 39. Position 10 is equal to 71. And then position 2 is equal to 37. Okay, that's actually really interesting. Something that just occurred to me, probably an optimization that we might need to do for part 2, or keep in mind for part 2, is that it looks like, or maybe even part 1, it looks like if we start at 0, we're going to get something, and then we go to 1, which it goes down, 2, which it goes down from 1, 3, it goes up, so it's only ever going to get worse once it starts increasing. So we can stop we can start from the lowest, and it should always, shouldn't it? It should always increase when, once it starts increasing, it's not going to start going back down, is it? Well, I guess we'll see if we need to do that optimization. Class submarine swarm, def initialize swarm positions, and we've got a def total fuel to position. Okay, and those tests fail now. We've got a swarm equals swarm positions dot split on comma map 2i, and actually I don't need to do 2 maps here. Map position, and this is where we need to require relative dot slash crab submarine, and do crab submarine dot new position dot 2i. And so now we've got a list of swarm. Let's change that to submarines. And then what we need to do is, the tests are still gonna fail, right? Yeah. Or fail for the same reason. Okay, so total fuel 2 becomes just submarines dot sum submarine dot, what's that even? It's total, it's fuel 2, fuel cost 2, fuel cost 2 position. And those tests should pass now, right? Yes. Okay, great. And now we need to determine the horizontal position that the crabs can align to using the least fuel possible. Okay. So what we can do is let's say, we've got a method, and let's describe, what is it? Cheapest fuel position, cheapest swarm position, and it is oh, it's not cheapest swarm position, it's, well, I guess we need to do cheapest swarm position, and then we get the total fuel to that position. Okay. It is 2 for that set. We could try coming up with other sets, but let's see if this is good enough for part 1 at least. Expect cheapest swarm position. Oops. Test swarm dot cheapest swarm position 2 equal 2. And right, fails. There's probably some other tests I could write, and if we were writing this to actually make this more robust, I'd probably write some more, create some more swarms to force the cheapest swarm position to kind of need to calculate, but or need to calculate this, because one way to make this test pass is to just make it return 2. But since we only have one set here, but in the interest of time, I'm just going to do this with this one and see if that gets us where we need to go. But what we would do is, let's start position is at submarines dot min submarine dot I need to open up the position. So get the submarine with the lowest position. Start position and end position equals submarines dot max submarine dot position. So it's actually dot position from what that returns. And then what we would do is let's get the fuel cost of the start position. So starting fuel equals total fuel to start position. And might as well do this optimization. Nope, it seems actually simpler to do or let's say current cheapest fuel, and or actually what we need to do is we need to have a position. We want to get the position, not the cheapest fuel cost. Well, current position equals start position, total fuel to current position, and while current cheapest fuel is new cheapest while current cheapest fuel is what do I need to do here? I'm trying to getting ahead of myself. Okay, so we've got the current position. We need to increment the current position, and let's say while current position is less than end position, or less than or equal to while current position is less than end position, current cheapest or cheapest position equals current position. And cheapest position equals current position if current cheapest fuel is less than total fuel to our current cheapest fuel is greater than total fuel to current position. And then we set current cheapest fuel equal to, or actually probably if current cheapest fuel is greater than total fuel to current position, then we set cheapest position equal to current position. We set current cheapest fuel equal to total fuel to current position. So there's an optimization there. We can memoize that so we don't have to calculate that twice, but it doesn't seem, at this point, it's and cheapest position, return that, and then we increment current position equals current position plus 1. We need to increment that every time. Yeah, so that should give us the number we expect. No, expected 2 got 16. Why is that? Did I not? If current cheapest fuel is greater than why would that be? Let's do see what's going on there. It's never getting to that pry. That's weird. Start position min. Why would swarm position? Let's see what values we've got here. Start position 16. Why is that? That seems wrong. Am I doing min and max wrong? Oh, I know what I did wrong. I need to compare them. Submarine A, submarine B, and submarine A, submarine B. So this actually gives two parameters, and you give it a way to compare the two. You can't just say value. So let's see if that's right. Start position and position, yeah. And let's actually see, I think that was the one bug that's keeping this from working. Yes, okay. And so if we do that, we know that that's passing. And then we just need to create another method, cheapest. What are we looking for? To align to that position. Cheapest fuel position, or cheapest fuel cost. Cheapest fuel position, cheapest fuel cost. It is 37. Expect test swarm.cheapest fuel cost to equal 37. And that's easy. We just do def cheap, can run the test here, right? And then def cheapest fuel cost is total fuel to cheapest swarm position, just to make the solution.rb a little bit easier. Okay, so now we require relative submarine swarm.rb, and then we input equals file.open problem input read. We do solution swarm is equal to submarine swarm dot new input, and we do puts total fuel cost to optimal, let's say optimal fuel cost. Solution swarm dot cheapest swarm position. Now let's see what we got. 330. How much fuel must they spend to align to that position? 330. That's not the right answer. The answer is too low. If you're stuck, make sure you're using your full input data. There are also some general tips on the About page. You can ask for hints in the subreddit. Please wait 1 minute before trying again. Okay, so 330 is too low. That's interesting. I wonder what we got going on here. Wonder what I missed. So it needs to use more fuel, but I found one that gets to 330. How did that happen? Let's do... Oh, that's right, because it's not cheapest swarm position, it's cheapest fuel cost. That's what I get for having a bigger API. Fuel cost, cheapest fuel cost. So that's more the fuel cost to get to 330. And I gotta wait a minute. Okay. So that's much too low, huh? Whoops. In the meantime, let's see, what could they change to make me need to do that optimization? Because if we're starting at 330, or if we're getting to 330, we're still doing all of the rest of, to 1579 at least, 1881. Still doing quite a few calculations where we could do, if it goes to 0 to 330, we can only do, 331, 332. So maybe there's a little bit more calculation that needs to go. It's going to need to go into the total fuel cost or something that makes it better to stop much earlier. But I guess we'll see. It's hard to guess. It's hard to guess where things are going to go. But did the first part in right about 35 minutes. Still running a little bit slower than yesterday, but feel pretty good about the implementation. Let's see if we're past the minute mark to try again. We are. Cool. Part 1's done. Let's see what part 2 has in store. The crabs don't seem interested in your proposed solution. Perhaps you misunderstand crab engineering? As it turns out, crab submarine engines don't burn fuel at a constant rate. Instead, each change in one step in horizontal position costs one more unit of fuel than the last. The first step costs 1, second step costs 2, third step costs 3, and so on. As each crab moves, moving further becomes more expensive. This changes the best horizontal position to align them all on. In the example above, this becomes 5. Cool. This costs a total of 168 fuel. This is the new cheapest possible outcome. The old alignment position 2 now costs 206 fuel instead. To determine the horizontal position the crabs can align to using the least fuel possible so they can make an escape route, how much fuel must they spend to align to that position? Cool. So actually, I guess that optimization also might not necessarily work. Well, maybe it will. Let's do something here, though. Let's make their part 1. Or copy input to part 1. Or actually, move solution RB to part 1. Move spec to part 1. Part 1, move text input to part 1. Copy part 1. Is this where I need the R? Copy our part 1 to part 2. Cool. That way we can preserve the work that was done in part 1 and start changing it to what we need for part 2. Okay, so part 2, we're going to change the total fuel cost tests for the crab submarine. And so this becomes, moving to 5, it is 66. And 16 still starts there, but the fuel cost of 5. Let's change all of these that we're moving. 24 up to 5. 16 now becomes 66 fuel. 5 moving from 2 to 5 costs 6 fuel. Moving from 0 to 5 costs 15 fuel. Okay, and so now in part 2, our specs, well, these 3 are going to fail, and then the other ones are going to fail, and we need to figure out what those should be. We can also run the tests to see what they should be to, if that still holds, that it's always either going to be increasing or decreasing. But maybe we don't even need to do that optimization. Okay, so total fuel cost 2 is no longer the difference in the positions. It is number of first step costs 1, second step costs 2, third step costs 3. 1, 2, 3. Each crab moves further. So that's, so it's 11. Let's say, is it the difference plus 1, or the difference times the new position plus 1? 4. Let's say 1 to 5 is 10. So it's 1, or no, it's the, oops, 5 factorial. That's not factorial. It's 1, 2, third step costs 3, and so on. So it's 1 plus 2 plus 3 plus 4 plus 5. Four times 6 is not 10, but 6 times 11, 66. Yeah, well, I can actually just do times, do number, zero, total equals total plus number, and then we return total, and that should give us more failures. Crab submarine spec. Oh, right. All right, so crab submarine spec is done. And then now we just need to change the swarm spec. We can cancel these out. What we really want to do is the old alignment position 2, and so let's append these for now while we make sure that this one solves correctly. It is 206 when moving to position 2, and we expect test swarm dot total fuel to, oh, actually we already have that test here. 206. 06. And append these for now. We'll fill those in later. Okay, cool. So that one passes. So that means cheapest swarm position should equal 5. And this is also 168. 168 and 5. Oops. Still passes. let's see if we can skip ahead without testing those other ones. I don't need to change the solution part, huh? Cool. Okay, so let's do ruby solution.rb and see what we got here. It is grinding. Okay. Do need to optimize. Fun. Okay. So let's see if the assumption from that first part is going to hold, that it should grow and then get smaller. So let's see what it is. Move these around. 1, 2, 3. So we know what it's going to be at 5. Oh, looks like it actually finished. Maybe I won't need to optimize today. That's the right answer. Cool. Day 7 complete in a little over 45 minutes. Wasted 1 minute to because of that first bug. But yeah, what I was gonna do, if that was gonna take forever, like yesterday's was gonna write some tests, see what came out for those numbers, and see if we could figure out some way to cut down on the amount of calculation we were doing, but didn't need to. But also, this code is up on GitHub. I realized I haven't been sharing that, so the link to the repos in the video description. Feel free to check it out. But I guess that's all I've got. Until next time, see you all tomorrow. Thanks for watching.